So we've talked about low mass, now on to high mass or massive stars. Low mass stars are only able to fuse to carbon in their core. What this means is that a white dwarf is primarily made of carbon. High mass stars have the pressure and temperature necessary to fuse elements beyond carbon. In fact, they'll make it all the way up until iron. Now, the reason why iron, if you remember back when we were talking about the nucleus, we mentioned that iron has the lowest energy or lowest mass per proton. What that means is you cannot fuse iron and have it release energy. Instead, fusing iron is actually an energy sink. It requires extra energy that you don't get back out. So high mass stars or massive stars are able to fuse elements all the way up until iron. Now, during this stage, they'll actually swell up and become thousands of times larger than their main sequence size. These are the red supergiants. If we were to replace our sun with one of these red supergiants, it wouldn't just go beyond the orbit of the Earth, it would also go beyond the orbit of Mars and all the way beyond the orbit of Jupiter in the solar system. These stars are incredibly large. Now, as they fuse in the core, every time they begin a new stage of fusion, they leave behind a shell of the previous stage. So right before one of these massive stars dies, it has a core of iron that is not fusing, with a shell of silicon fusion, a shell of oxygen fusion, a shell of neon fusion, a shell of carbon fusion, a shell of helium fusion, and a shell of hydrogen fusion. All of this means there's a lot of pressure, which is going to cause the star to swell out. Now, eventually, the core is going to get so large that gravity beats everything. When this happens, the core is going to suddenly begin to collapse. As it collapses, electrons are pushed into protons, which then turns them into neutrons. Now, during this process, as the core collapses, the rest of the star then explodes. This is what we see as a supernova. In these two images, we're actually looking at two supernova remnants. You can see the destruction that these things have created for the outer layers of the star. Now, during this supernova, there is so much excess energy that we're able to fuse beyond iron. Remember, a normal star during its normal fusion processes is not able to fuse iron because it has the lowest mass per proton. However, if during a supernova we've got so much excess energy, we're able to produce everything else. What this means is in astronomy, we can actually explain where all of the elements come from. So hydrogen and helium and a little bit of lithium, all of these are actually produced during the first few minutes of the universe, during the Big Bang. Everything from helium to iron is fused in stars. So low mass stars convert hydrogen into helium and then helium into carbon. High mass stars will then go beyond carbon and fuse all the way up until iron. Then, during a supernova explosion, all of the rest of the periodic table is formed. Okay, so for what this means is something like gold actually formed as a star exploded. So a star exploded, sent all of its bits out into space, which then mixed with the interstellar medium. The interstellar medium cooled and formed into dark nebula. Within the dark nebula, stars were then able to collapse and form. And if you remember last time, it is possible around those collapsing forming stars to get protoplanetary disks that form into planets. Well, those planets will have those same things that came from the exploded star. So, at least on one of these planets, life has developed, and we go around digging gold up out of the ground and giving it to each other as presents. What this means is the next time that you give somebody jewelry, you can tell them you're actually giving them a piece of a star, because that's where it had to come from. That's one reason why astronomy is the best science. All right, so the thing that is left behind after the core collapse, we have the outer layers expelled as a supernova remnant. But down at the center, there are two possibilities. One is that it will have collapsed into what we refer to as a neutron star. A neutron star is a star that is composed almost entirely of neutrons. Now, neutron stars we expect to be about the size of a city, having a diameter close to about 20 kilometers across. But these will have masses between 1.5 and 2.5 times the mass of our sun. So imagine taking 1.5 suns or 2 suns and squeezing it down to the size of Orem. That's how dense these neutron stars are. These are the densest objects that we know of in the universe. Now, the way that we've actually discovered these is that some of them appear to blink. Now, they're not actually blinking. Instead, they have beams of energy that are streaking away from them caused by their magnetic field, and the star is rotating, which means that this beam sometimes points at us, and so we see it, and sometimes it's pointing away, so we don't. So it's similar to how a lighthouse works. If you're very far away from sea, you see the blinking of the lighthouse. The lighthouse itself is not actually blinking, it's a beam of light that's sweeping around, and if it's pointing at you, then you see it. These types of neutron stars, where we see them blinking, are referred to as pulsars. Now, for very high mass stars, what are sometimes referred to as supermassive stars, they're going to leave the main sequence and evolve into supergiants, just like the massive stars. However, when their core collapses, the gravity of the core is going to be so great that there is no known force that can stop the crush of gravity. All of that star's mass gets squeezed down to a single point, meaning that it has mass, but it now has a volume of 0. And if you've ever taken math, if you've tried to divide by 0 and found you can't, that's what's happening here. Okay? This thing that forms where all of that material collapses to a single point is what we refer to as a black hole. So a black hole is what remains from a supergiant star as its core has collapsed. Now, the reason why we name it a black hole is because its gravity is so strong that light cannot escape. We'll touch on that more in just a second. But first, why is its gravity so strong? If you remember back, gravity is one of these inverse square laws. So here we have one planet with a person on it. At the surface of the planet, this person weighs 10,000 newtons. That's actually really, really high. This is why this is an indestructible person. Otherwise, there wouldn't be a person anymore. But this indestructible person has a weight of 10,000 newtons. If we reduce the radius to half, okay, so we shrink it down, leaving the mass the same, so the only thing that's changing is the distance, then, because it's an inverse square, 1/2 squared is 1/4, but it's inverse, so we have to flip it. The gravity increases by 4 times. So the person was at 10,000 newtons at 1 full radius. At half a radius, they're now 40,000 newtons. So the smaller it gets, the crazier, the stronger the gravity becomes. So as we look at a black hole, we have the point at the center where all of the mass is contained. This is what's referred to as the singularity. Often in math, if there are times where we have to divide by 0 or we see the function blows up, we refer to it as a singularity. So this is the singularity at the center of the black hole. Now, at some distance away from the singularity, we're going to reach a point where the escape velocity is going to equal the speed of light. The escape velocity is how fast you have to go to actually escape, to get out of the object. Anything that is closer to the singularity than this distance will have an escape velocity faster than the speed of light, which means that the object will not be able to escape. At the event horizon, the escape velocity is the speed of light, and beyond the event horizon, it is less than light. So what this means is that no light can escape from beyond the event horizon, which is exactly why it has that name. Anything that happens beyond or closer to the singularity than the event horizon is blocked from our view. We cannot see it. It is beyond our horizon. Now, anything that is beyond the event horizon will be able to escape, so it may be possible to see it. However, the speed is going to be really, really high, near the speed of light, if it is really close to the event horizon. Here is our fourth clicker question. If the sun collapsed to become a black hole, the orbit of Earth would, so this is by magic. So there was sun and then boop, it's gone. We have a black hole that's the same mass as the sun, but it's a black hole instead of the sun, but the same mass. Okay, so if the sun collapsed to become a black hole, the orbit of the Earth would A, remain unchanged, B, be pulled inward toward the black hole, C, spiral outward away from the black hole, or D, be a straight line path. Go ahead and think about it, and we'll discuss in just a bit. All right, what do you think? So the amount of mass has not changed, and the distance has not changed. Those are the two things that gravity worries about. So if the distance and the mass haven't changed, then gravity hasn't changed, which means that the orbit is going to actually remain the same. So the correct answer is A, and it's all because of how gravity behaves. We often get this idea in popular culture of black holes as these giant cosmic vacuum cleaners that sweep up and destroy everything. That's not actually the case. They still obey all of the same normal laws. Now, what does happen is if you get really close, weird things happen and things get pulled in and stuff gets destroyed. But at large distances, even not that large of a distance, everything still remains normal. For example, if you have a black hole that's about 3 times the mass of the sun, if you're around a few thousand kilometers away, nothing's actually that strange. Things are still behaving relatively normally. You're not actually in danger. And so don't actually worry about black holes. They're not going to be a huge problem for us.